This is for 2.6 for limits at infinity. And first we're going to go over the rules for horizontal asymptotes. So if the power at the top is less than the power at the bottom, then there's a horizontal asymptote at y equals 0. If the power on the top is equal to the power at the bottom, then there's y equals the ratio of the coefficient in front of the greatest power at the top divided by the coefficient in front of the greatest power at the bottom. If the power at the top is greater than the power at the bottom, then there is no horizontal asymptote. Now, there's an exception. If the power at the top is greater than the power at the bottom by 1, then there's a slant asymptote, where it's the quotient of the expression. The basic idea to take away from this lesson is that as the limit approaches negative infinity or infinity, the function will approach its horizontal asymptote in that direction. So to solve for limits at infinity, what you need to do is find the greatest power of x at the bottom and divide both the numerator and denominator by that power. So for example, if we have 2x plus 11 over 3x, the greatest power is x at the bottom. So we're going to do 2x divided by x plus 11 over x over 3x over x, and this is as the limit approaches infinity. And now what this simplifies to is 2 plus 11 over x over 3. Now, any constant over infinity is going to equal 0. So as the limit approaches x, when we plug in infinity, it's going to be 11 over infinity, which will be 0. And then by simplifying that, we will get 2 over 3. So this means that the horizontal asymptote of the graph is at 2 over 3 as x approaches infinity. Now a little trick you can do is that you don't always have to solve it like this. For this equation, since the power at the top and the power at the bottom are the same, by using the horizontal asymptote rule, we know that it's the ratio of the coefficients. So if you want to check your answer, you can just try to find the horizontal asymptote by itself. We can check our answer by graphing the function, and if we look at over on the right side as x approaches infinity, it's going to approach the horizontal asymptote of 2/3, and that means that as x approaches infinity, it's going to equal 2/3, which confirms our answer. Now for this expression, we're going to solve it and simplify. So if we go here, the largest power at the bottom is 11x to the third, so we're going to divide both the top and bottom by x to the third. So this is going to become 3x to the fourth divided by x to the third, plus 5 over x to the third, all divided by 11x to the third divided by x to the third, plus 2 over x to the third. Now after we simplify this, we get the limit as x approaches infinity equals 3x plus 5 over x to the third over 11 plus 2 over x to the third. Now, after we simplify this, we'll get the expression 3x over 11. Now, a little side note and a common student mistake is that sometimes they treat infinity like an actual number, but it's not. It's an idea. So because of that, we can't subtract infinity from infinity. That does not equal 0. That is wrong. But if we multiply infinity by infinity, that will equal infinity. So we cannot add or subtract infinity, but we can multiply. So for trig functions such as arc cotangent x as x approaches infinity, we don't have an algebraic way of solving this, but we can just use the original method of finding the horizontal asymptote to determine what this limit is. So here we have the graph of arc cotangent, and it's bounded by pi over 2 and negative pi over 2. And by looking at this graph, we can tell that as x approaches infinity, it's going to approach this asymptote of negative pi over 2. So therefore, this function is going to equal to negative pi over 2. Now, for finding limits at infinity and negative infinity are usually the same, except for this special exception when there's a square root. Now, first off, when we divide everything by the largest power at the bottom, we're going to get 5x over, here's the exception, x, because even though this is x squared, it's inside a square root. So when we take it out, it will just be x over root 2x squared over x squared because it's still inside the square root, plus 1 over x squared. So you need to keep that in mind. A lot of students forget this. And now, since this is negative infinity, we're going to have to add a negative at the end. After we simplify, we'll get 5 over negative root 2 plus 1 over x squared as a limit of x approaches negative infinity. And then when we solve for this, we'll get 5 over negative root 2. And that is for when it approaches negative infinity. So by looking at the graph of this function, we can see why we need to add a negative on the outside of the square root. And it's because, as you can see, as x approaches negative infinity, it approaches negative 5 over root 2. And as x approaches infinity, it approaches positive 5 over root 2. And that's why when we have a square root, and it's approaching negative infinity, we need to add a negative in front. So for this expression, we can't simply just plug in negative infinity because of the rule I said earlier where you can't add or subtract infinity from each other. So what you're supposed to do is multiply by the conjugate like so, simplify the expression. Now, before you forget, this is x minus, but you're going to have to change to a plus because this is negative infinity, so it's going to be x minus negative root. So that becomes a positive. And then when we divide it by the largest power, it is not x squared, it is x, because remember the x squared is inside a square root. So when we do that, we'll be negative 5x over x over x plus root x squared over x squared, because now it's inside the square root, plus 5x over x squared. Once we simplify that and add in the limit, it will be negative 5 over 1 plus root 1, which will become negative 5 over 2. And that is the limit at negative infinity. A recurring question on the AP test is to solve by squeeze theorem for limits at infinity. So this is the same thing as when we solve for a regular limit, a limit using squeeze theorem. So it would be cosine x bounded by negative 1 and 1. And then we'll change this to negative 1 over x, cosine x over x, 1 over x. And then we'll find the limit of both sides. So it will be limit as x approaches infinity for negative 1 over x, which is going to equal to the limit as x approaches infinity for 1 over x, because these will both just simply equal 0. Now when we do this, it will be 0 cosine x over x and 0. And by using squeeze theorem, we can conclude that the limit as x approaches infinity for cosine x over x is 0 through squeeze theorem.